Okay, so for 2011 5, we have beginning of 2010, we got a landfill that contained 1,400 tons of solid waste, and the increasing function W models the total amount of solid waste stored at the landfill. Planners estimate that W will be satisfied by the differential equation given, which that dW dt is 1/25th W minus 300 for the next 20 years. Keep in mind that W is measured in tons and the T is measured in years from the start of 2010. And in part A, it says use the line tangent to the graph of W at time 0 to approximate the amount of solid waste that the landfill contains at the end of the first 3 months. And they give you a nice hint there that time is a quarter, so you don't put 3 in there for 3 years, 'cause it's not years. So bottom line here is if we have this function W and we want to write an equation for a line tangent to it, then ultimately we're going to start out by writing on point slope form. We know that at this point, and again we're looking for the tangent at time 0 here, so the original t here, keeping in mind that x is really t here in this problem, is 0, so ultimately we'd have mx on this side, and then we'd have y minus 1,400 on this side, because the original amount of stuff is 1,400. So that would be that, and then the m, of course, is going to come from our derivative. So in our derivative at this point, we have the value here, our w value here would be the 1,400 also. Okay. So that means our 1,400 here will give us 1,100, and actually the w is the amount of waste that we have, right? Yeah, how many? 1,400 tons. So that W in here is going to give us that 1/25th, and then 1,400 minus 300, or times, not equals. So we get 1,100 over 25, okay, which ultimately 25 goes into anything that ends in anything that's divisible by 100. So 25 and 40 would be 1,000, so 4 more would be 44. Okay. All right, so 44 would be our slope, so y minus 1,400. 44x, and so our equation, our tangent line would be 44x plus 1,400. So again, ultimately, we're just writing an equation for a tangent line. We know the initial point here, we know a point, at least we know that at when time is 0, the amount of waste is 1,400. We also can find the derivative here. The derivative, again, remember, is not based on time, it's based on w. That's why we put w in here, not times 0, because it's not in terms of t, it's in terms of w. So that's why our 1,400 will go in there again. And then ultimately, again, once we calculate that slope and so on, we'll be able to write our equation correctly. So this is our equation. And the final part here says how much is in there, using the tangent line, how much is in there after a quarter of a year. So if we go 44 times a quarter, we get 11 plus 1,400. So ultimately we get 1,411 tons. Spell it right. So 1,411 tons. All right. And ultimately that part A is worth 2 points. 1 for finding the derivative. So if you got that 44 derivative, point for that. And then a point for getting the right answer. Final answer, 1,411. Questions on that one so far? All right, let's take a look at part B then. What do we got there? It says we got d squared w dt squared in terms of w. So find the derivative of that equation that we were given, the differential equation. We got 1/25th w minus 300. All right, so ultimately, if we want to find the second derivative of this, we get this would be the derivative of both sides with respect to t, of course. So the derivative of this side with respect to t is going to be Keep in mind, if you want to, you could write this as 1/25th W minus 300 divided by 25 would be 12. Okay. All right. Keep in mind though that we're doing dw dt, or d squared w dt squared. Is again, it's the second derivative with respect to t. So if we take the second derivative with respect to t, is it just going to be 1/25th? It would actually be 1 what? So we're doing it with respect to t. This would ultimately be the derivative with respect to w being the independent variable, wouldn't it? So it'd be 1/25th, but we have to multiply by the derivative of w, which is dw dt. So we got to make sure we're careful that we use the chain rule on that, because ultimately, again, if we have our function in general, we have the independent variable being t, which is not the variable in question here, it's w, so we got to account for the fact that there's a chain rule issue here, knowing that w is a different function other than t. Alright, so the next part then is once we find that, it says use that second derivative to determine whether the answer in part A is an underestimate or an overestimate of the amount of solid waste the landfill contains at time 1/4. So ultimately what we want to know, this being the second derivative here, if we were to look at the second derivative, remember, well, the issue I guess is this: we have an increasing function, so really we have two choices. It could be increasing and concave up, in which case the tangent line that we wrote the equation for would be above the curve at a particular point to the right. True? Or it could be that shape where the tangent line to the curve would be, if we drew a tangent line to the curve, it would be beneath. So in other words, in this situation it would be an overestimate. In this situation it would be an underestimate. So ultimately, what's the difference between the two curves I drew? The concavity. So if it's concave up, what we found is going to be, or if it's concave down, I should say, this picture. If it's concave down, the estimate we made is going to be an overestimate. If it's concave up, then our estimate that we had from our line here that we created was it's going to be an underestimate. It's going to be below the curve. So let's see if we can determine that. So we need to, I guess, take a look at our second derivative that we found here. And if we do our 1/25th times dw dt squared, I guess the question is, what do we note about the derivative when we're at 0? In fact, all the way from 0 to 1/4, we're going to be putting 1400. Remember, keep in mind that we don't want to put time in here. We're not going to put 0 in here. But how much stuff is in there at 1400 in there, right? So that means that our dwdt at that point would be positive. So if we have positive times positive, that makes our dw dt, or d squared w dt squared, second derivative, greater than 0. Okay. Which means that it's what? Be this picture right here then, wouldn't it? It's concave up, so the second derivative is positive, because if we put in our, at the time in question, our derivative would be positive, times 1/25th. Okay. It's going to give us a positive second derivative, and with that being the case, we're going to get a underestimate, because the line that we drew will be underneath the curve as such. Okay. All right, so ultimately the point breakdown, 1 point for getting the second derivative. Okay. And then keep in mind, just as use that to determine whether it's an underestimate or an overestimate at that point. Okay. Like I said, since the second derivative is greater than 0, the curve itself will be concave up. So it would be an underestimate. All right, questions on that one? Let's see. Part C, actually, you know what? I think we missed something here. I see it. Keep in mind that this is the derivative, right? And so that is dw dt. So Actually, we didn't really miss it. Never mind. We're okay. Ultimately, the derivative of this is, of course, just 1/25th, okay, times dw dt. So, and we don't really necessarily have to put in dw dt in here to figure out the fact that it's positive. I mean, you can if you want to, I guess. They showed it in the answer that they actually replaced the dw dt with what dw dt is equal to. There's really no good reason to do that necessarily, because we know that it's right above us anyway. We can show that if we put 1400 in there, we're going to get something positive. So you don't really have to rewrite that. Okay. All right. Let's carry on then to part C. We have a differential equation to solve here. So part C, we have dw dt, 1/25th, w minus 300. And the initial condition here, of course, is w of 0 equals 1400, which we already knew that. And our job here is just to find the particular solution. We're going to find w, knowing that this is our differential equation. And keep in mind that the first two are 2 points each. That means this is 5 points, which in general for us should mean nice. We have a partial separable differential equation right here. They usually make that worth 5 or 6 points. That's good, because this should be fairly easy points for us at this point to solve a differential equation. So if it's not, got lots and lots of practice problems if we're still not there. But ultimately, if we were to get the w stuff on the left side with dw, and leave the 125, leave constants on the right, always with our whatever variable it is, t or x. And ultimately, if we do that part, that part's worth a point. So 11% of the problem is just separating the variables. So nice, right? Hopefully it'll be the same thing on this test that we take. All right, anti-differentiate both sides here. We're going to get natural log of absolute value of w minus 300, 1/25th t plus c. Another point. The fact that you have a constant of integration, another point. So point one you better clean up on, right? Easy points for us with as much experience we have with these kind of problems. So, and if after that, we need to use the initial condition to find c here. So if we do natural log of 1400 minus 300, and c would be on this side, so ultimately we get natural log of 1100 over here equals c. So using the initial condition, another point, finding the correct c. And of course the final point is going to be for making sure we solve correctly for w here, and the resulting sentence, which remember we'll go back to the sentence, is w 1 over ln of w minus 300, 1/25th t plus ln of 1100. And if we solve that for w, compose both sides with e. Get w minus 300 over here. We'll get e to the 1/25th t. And remember the algebra of this, when we have that situation where there's an argument that's a plus here, we use our laws of exponents. 3,300. So we'll use our laws of exponents to rewrite it as 1/25th t and e to the ln of 1100, which ultimately allows that to become what? Yeah, this is just 1100. So solving for w, we get 1100 out in front, e to the 1/25th t plus 300. And 1 point for the final answer correct. Questions? All right, well, let's take a look then at number 6. So for number 6, we have a function f of x equals sine x squared plus cosine x And we also have the graph of the absolute value of the fifth derivative of f. Keep that in mind. May or may not need that right now, but ultimately we have a graph of the fifth derivative, so keep that in mind. And part A here says write the first four non-zero terms of the Taylor series for sine x about x equals 0. So ultimately the first four non-zero terms of the Taylor series about x equals 0 for sine, isn't that one of the ones on our list that we didn't have to memorize when we did it the first time?
Awesome.
But what did I tell you before? For the test we will need to memorize it. But remember, you really don't need to memorize it, because ultimately, how is it built? F of 0, what's sine of 0? 0. What's f prime at 0? Sine's derivative is cosine. So cosine of 0 is 1 x. F double prime at 0 is negative sine of 0, which is 0. F triple prime is going to be negative 1. And remember, this is our constant term, x squared term. This will be our x cubed term over 3 what? Over 3 factorial. And we want the first four non-zero terms, it says, so we need to keep going, of course, here. But ultimately, this is the easy one, because all it's going to do is alternate between 0, 1, and negative 1, and so on. So the next one, of course, is going to be 0, and then it's going to be 1 again, and it's going to be x to the fifth over 5 factorial, and then 0, and then this one will be x to the seventh over 7 factorial. So ultimately be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial. And if you do that correctly, you get a point, which is not terribly surprising, because that should be hopefully on the easy side of questions that we have. Alright, and next it says write the first four non-zero terms of the Taylor series for sine of x squared about x equals 0. And ultimately we know that if we have the sine already, what are we going to do with the x squared to get our new one? Plug it in for x. So ultimately we should get x squared. This will be x to the sixth over 3 factorial. And then x squared in here would give us x to the 10th. X squared in here would give us x to the 14th. And if we do that correctly, we get another point. So again, if this is sine x, then this is sine of x squared. Replacing the x's with x squared, and we get a new Taylor series, and that is the correct Taylor series for sine x squared. Questions so far? Alright, and they give us in part B, it says find the first four non-zero terms of the Taylor series for cosine x about x equals 0, which again, another fairly free point for us. If we do the same thing with cosine, we're going to wind up with 1. And remember, all it is just the other terms that this one doesn't have. So we're going to have an x squared term over 2 factorial, and x to the fourth over 4 factorial, and x to the sixth over 6 factorial. And then just keep in mind that our signs here, we've got to be careful with our signs, because the first one comes from cosine. Then it comes from the derivative of cosine, which is negative sine. But then when we differentiate negative sine, we get negative cosine. So ultimately that first one will be negative and positive. Okie doke. Questions on that one? Again, just 1 point for that. Right. And then the other part says use this series and the series you found for sine x squared in the first part to write the first four non-zero terms of the Taylor series of f about x equals 0. So, keeping in mind that the f function is sine of x squared plus cosine x. So what does that tell me that we're going to do with the two that we just found that are essentially these two right here? And we're just going to add them up. So if we add them up, we're going to get 1, of course. Combining like terms here, we have both x squareds and these two. So we're going to get 2x squared over 2, so it'll just be, oh, I lied. Actually, those two would be, oh, no, never mind, this is a negative 1. So we'd have a 1 and then a 1/2, if you will. The 2 factorial is just a half. So if I have 1x squared and I have a half x squared, that's going to be plus a half x squared. And then the next term would be the fourth degree term, so it'd be plus x to the fourth over 4 factorial. And then we can combine the sixes. With the sixes, we have a negative 1. This one right here would be a negative 1/6, x to the 6th. 6 factorial would be positive 1/720th, x to the 6th. And ultimately, if I made this into a 720, 6 times 120. True. So 6 times 120 would give a 720. So 120 over 720. Alright. And actually those are both negative. Okay, put a positive here, that's actually a minus also. Both of those terms are negative. So if we put those two together, we get negative 121 over 720. X to the 6th. And ultimately, you got all those parts, 2 points more. Nice. Like I said, and really in the scheme of things, that's 5, actually 6 points so far that we've had here. 1, 2, 3. Or did I miss one here? 2 for this one. Oh, it is 2. Yeah, it is 2 for that one. That one's 2 also. Geez. More generous. Nice. So, like I said, 6 points with fairly simple Taylor polynomial manipulation. And that was on last year's test, so hopefully they'll be nice and put another one like that on this year's test, right? Okay, so go ahead, Matt.
I thought with the first 4 non-zero, I thought we would just go with it when you get to the x to the fourth. What
The difference between the first 4 terms,
okay.
or the first, the other phrase that we used in the past was indicated a degree. So the first to fourth order is what the term was that our book uses. So if they said the fourth order polynomial, then we would have only went to this point here. Yeah. So, but yeah, if they tell us a specific number of terms, then it doesn't matter how large the degrees are. So, good question. Anything else before we move on to part C? All right, let's see if we can figure out part C here. We got find the value of f6 of 0, and ultimately f6 represents the 6th derivative. True? Remember, going back to what we just did right here, this right here is our function, right? This right here is the 6th degree Taylor polynomial that represents it. True? And remember, in general, that x to the 6th term over 6 factorial, that part's there, and what part goes out in front of it? Isn't that the 6th derivative at the point in question? Okay. Remember, what number goes out in front of here? F of 0. What number goes out in front of x to the second, or x, I should say, for the first one? F prime does. What goes out in front of x2 over x factorial, or 2 factorial? F double prime. And what coefficient is on the cube, and so on. So whatever coefficient, whatever power we have here for our particular term, or whatever degree term, the 6th derivative, if you will, the nth derivative is always in front of the nth powered term, which is x to the n over n factorial. This is always f n, which means the nth derivative of n at that particular point. So really, if we compare these two, then we can answer the question right here, I guess. So might as well put it right here since we have it. Ultimately, this right here, this is the term. True? And so therefore, we can see that that 720 right there is 6 factorial. So ultimately, wouldn't I just have a negative 121 out in front of it? Again, this is the 6th term. The term part of it is this. The derivative part is anything else. Fair enough? So what's our anything else in this case? Be negative 121. So if we can recognize that, then our answer then is going to be negative 121, and we'll get 1 more point for recognizing that. All right. Questions on that one? All right. Let's see what we got here in part D. Looks like we got some kind of remainder estimation issue. So let's see what we can do here. It says P4 is the 4th degree Taylor polynomial for f about x equals 0. And it says use the information in the graph of the absolute value of the 5th derivative of x up above And we want to show that, that P4 at a quarter minus F at a quarter, which remember, don't get bogged down with the notation here. All this is the difference between the polynomial and the actual function. So really, this is really the what? It's the error. Right? It's how far apart the actual answer is and our polynomial estimation answer. True? So like I said, don't get bogged down just because it looks not very nice. Okay? All it is the error. It's the difference between the polynomial and the function. That's the error. That's how much difference there is between the two. And ultimately, we know that at 0, at the center point, there's going to be no error. True? But as we go away from the center point, what happens to the curve of the polynomial? They start to what? They start to come apart. Okay? There starts to be some error. Okay? Now, ultimately, keeping in mind that, and again, all we're trying to show is that that error is less than 1 over 3,000. Alright, so the issue then is, can we, and keep in mind they gave us a picture of the fifth derivative, and that kind of should ring a bell here, because if we're talking about P4, we know that the error estimation has to do with the n plus 1th derivative, and we have a picture of the fifth derivative right there, don't we? So remember, our general formula here is m. Remember, m is the maximum value of the nth derivative, n plus 1th derivative, I should say. And then remember, we have x here to the n plus 1 over n plus 1 factorial, and that right there gives us our error estimation. So for us, what's going to go in the x? Well, we want to do this at a quarter, so that's our x value. Remember, they asked us for the error at a quarter, so that's going to be the x value in question. And then what about m? There was a reason they gave us that fifth derivative picture. True? Remember, m stands for the maximum value of the nth plus 1th derivative. So if we look at a quarter in our picture there, okay, what does it look like the value is of our n plus 1th derivative? Looks like it's about 30 some, doesn't it? True. So let's say we use 30 then for our m, and let's see what happens. So this being a non-calculator problem, we're going to have to use a little bit of arithmetic here to figure out what these numbers are here. But ultimately, if we did 4 to the 5th power, we know that 4 to the 3rd power is it's 4 times 2 is 16, then 64. 64 times 4 will be 256. So 256 times 4, 24, 2024. So this would be 1 over 1,024 times 5 factorial. We know 5 factorial is 120. Keep in mind we also have 30 up here that we're going to deal with. Alright, and then if we cancel those two out, we're going to get 30 and 120. Those will make 40. So we'd ultimately have 1,024 times 40. And if we do 1,024 times 40, we're going to get 4,096. So the question is that true sentence there that we've just shown? Is 1 over 4,096 less than 1 over 3,000? Is 1/3 less than 1/2? Did I miss something? Oh, you're right. Sorry, that should be a 4. So, and actually then that's still 4,096. It would have been 40,096, 960 if I kept the 40 on there. So ultimately the question is this true then? Is 1 over 4,096 less than 1 over 3,000? Absolutely. Alright. So with that, we got ultimately two points for that. One, if you had the correct form of the error bound, which is ultimately this part right here. And then number 1, if you showed that it was, or another point, if you showed that it was in fact less than 3,000. All right. So I guess the bottom line is that for this, this general formula right here, and again, 5 actually is n and n plus 1 and n plus 1 factorial. Really, the only time that we're able to use that particular formula to do a calculation is if we can find m. True. If we have no means to find m, then there's really no way we can do anything with that, is there? Okay. But the fact that they gave us the n plus 1th derivative gave us means to find m, didn't it?